Welcome to the lesson on section 8.4, Integration by Partial Fractions. In this lesson, you'll learn techniques for using polynomial long division and partial fraction decomposition to evaluate integrals. In the first example, consider the integral of 2x to the third plus 3x squared plus 7x plus 4 over 2x plus 1. When the numerator has degree greater than or equal to the degree of the denominator, we'll use polynomial long division to express the fraction as separate terms. Start by dividing the first terms and writing the quotient up top. Multiply this quotient by the divisor and write the product underneath. Subtract and bring down the next term. Then add the remainder as a fraction over the divisor. So our original rational expression is the same as x squared plus x plus 3 plus 1 over 2x plus 1. We can use the power rule to integrate the first three terms and use natural log to integrate the fraction. In the second example, the denominator has greater degree than that of the numerator. Substitution doesn't look like it'd work here. If we let u equal the denominator, we would need 2x minus 3 as the du, and I don't see how I could change the existing x plus 3 into a 2x minus 3. The method of partial fractions can help me rewrite this rational expression as the sum of rational expressions with simpler denominators. First, factor the denominator, and each factor becomes a denominator of a partial fraction. You may recall from pre-calc that because each of these factors is linear, it's paired with a constant numerator. Multiply both sides of this equation by the common denominator. So we need to solve for the constants a and b in the equation x plus 3 equals a times x minus 2 plus b times x minus 1. From here, you may have seen two different methods of solving for the constants. One method is to simplify the right-hand side and gather the like terms together. Instead of this, I usually prefer to substitute numbers in place of the x's, hoping to eliminate one constant and solve for the other. For example, if I let x equal 1, I can see that the b will drop from the equation. 1 plus 3 equals a times 1 minus 2 plus b times 1 minus 1. So a equals negative 4. Substituting 2 for x causes the a to drop from the equation, so b equals 5. Now that I know a equals negative 4 and b equals 5, I can rewrite the original rational expression as negative 4 over x minus 1 plus 5 over x plus 2. Both of these fractions have natural logs as their antiderivatives. The next example shows how to deal with repeated factors in the denominator. When factors are repeated, there should be a partial fraction representing every power of this factor from 1 to the exponent that appears in the problem. You might think at first that the x squared looks like a quadratic factor, but instead it's considered to be a repeated linear factor, x times x. Thus, the partial fractions with x and x squared in their denominators will have constant numerators. Multiplying both sides by the common denominator, I get 3x squared minus x minus 3 equals ax squared plus bx times x plus 1 plus c times x plus 1. Plugging in negative 1 for x causes the b and c to drop out, so a equals 1. Plugging in 0 for x makes a and b drop out, so c equals negative 3. Now I'm out of x values that cause constants to drop out of this equation, So I'll just pick another number that I think is easy to work with, like x equals 1. So when x equals 1, the left side becomes negative 1. And on the right, I know that a is 1, and 1 squared is 1. 1 times 1 plus 1 is 2, so the next term is 2b. We already found that c is negative 3, and 1 plus 1 is 2. So solving this equation for b gives me b equals 2. We just found that a equals 1, b equals 2, and c equals negative 3. To integrate the 3 over x squared, I would think of that as 3x to the negative 2. So integrating gives me the natural log of x plus 1 plus 2 times natural log of x plus 3x to the negative 1 plus c. This example has a quadratic factor. The quadratic factor must be topped with a linear numerator. Thus, my partial fractions will take on the form a over x minus 1 plus bx plus c over x squared plus 2. I get this from multiplying by the common denominator. And I plugged in 1, 0, and 2 for x to solve for the constants. So a equals 1, and b and c are both negative 1. The first fraction will integrate as a natural log, but I'll split up the numerator in the second fraction. In the one that says x over x squared plus 2, I'll be able to integrate that by substitution. If I let u equal x squared plus 2, the du would be 2x dx, and I can make that happen. In the 1 over x squared plus 2, I would apply a trig substitution using the identity 2 tan squared theta plus 2 equals 2 secant squared theta. But we won't finish the rest from here. In this example, I'll show you how to set up the partial fractions with several different types of factors. The x cubed is considered to be a repeated linear factor. So we'll need a fraction for each power from 1 to 3, and the numerators will all be constant. X plus 1 is a linear factor, so it gets a constant numerator, and x squared plus x plus 4 is a quadratic factor, so it gets the linear numerator ex plus f. The x squared plus 3 is a repeated quadratic factor, so I need to represent every power of that from 1 to 2 and top each of those fractions with a linear numerator. This concludes our lesson on section 8.4, integrating by partial fractions.